Hello everyone, welcome to this first lecture on fluid mechanics, applied fluid mechanics, MET 313. Uh, in this lecture I'm going over some of the things that we have covered on Monday, and then we will start the basic information or the basic definitions that we're going to need in this course, such as the definition of fluid, what are the types of fluid that uh, you will need to deal with. Before we do that, let's review some of the applications. I know this is just a quick review of some of the applications. If you think about fluids, you might think of anything that's around you. Some of the applications that I'll be mentioning today is first, for example, aviation, how we can create lift for an airplane. So how does that happen? We will need to study something called the Bernoulli equation, the energy equation, the difference in pressure and density, and the kinetic energy. Other applications, for example, maybe you have thought about it before, maybe not. It's oil and gas, or for example, any piping system. So for example, we have this piping right here, and we need to transfer oil, any fluid, through this, or it might be simply a building or a well. So we have a building here, and we need to transfer a certain amount of water, for example, or any fluid, gas, into different floors here. So first we have the piping right here, and then we have the driving unit that drives and pumps the liquid through the pipes. So we need a pump, for example. If it's air, then we're gonna need a compressor. And then we have the piping system right here. So we need to know how to calculate the frictional losses inside these pipes, so that we can select the proper pumping unit that satisfies the needs of the application that I'm working on. Other applications that I thought of is the air conditioning, or the HVAC, HVAC system. For example, you have air here, warm air, and then we need to take the air, get it into the building, provide cooled air. Then we have refrigerant running between the unit that's inside the house or the apartment and the outdoor unit. So again, we have frictional losses, we have pumps, we have liquid here, or you might think of the radiator of the car. So you have a fan here, and then you have piping system going into the, let's say that's where the block unit of your engine, and then you have water or the cooling liquid running here. So again, you need to figure out what's the pump requirements here and how much air you need here, so that you achieve the cooling that you have in the system. Other applications that are really related to this course are, for example, we have a piping system, and we need to measure pressure right here. We need to measure the flow rate. So we're gonna deal with some kind of manometers right here. So we have another liquid here. So if you have, let's pick another color. Doesn't want to do it. Okay, let's first erase those. Okay, that's enough for now. That's lost too much time. So if we have fluid going in this direction, and we need to tell how much fluid is going here, so we will learn how to measure that using some kind of a pressure unit system. So we will look into the pressure difference between 2 points, here and here, 1 and 2. So we'll be looking into delta P, pressure difference between those 2 points, and we will learn how to relate this pressure difference into how we can get the flow rate of the fluid, or whatever kind of fluid here, into the flow rate based on the pressure difference that we have. Other applications that I'm sure you have seen this, the car lifting or jack of your car. So for example, sometimes you put a small force here, let's say for example F1, 50 Newton here, and that's section 1, and over here we have section 2. So with the application of fluids, we can actually get F2 right here, much more, much higher than this one, based on, or the vice versa. We can put another force here, and then we can change the area so that we can decrease the force. So if you put here, you're gonna need here at the end 5 newtons. If this one, the ratio between the two areas is 10, for example, A2 equals 10 times A1, we will see that the relation between those two forces is actually 10 times. And that's, I am sure you have seen this part of it in physics. It's basically P equals force by area. And we have here a liquid, oil for example, and assuming that there is no leakage, so we will assume that this oil or this fluid is incompressible, so it can't be compressed, so the volume that it has, it can't be changed. So once you change the area, the pressure has to be the same, so you change the area, then the force will change inversely. If you increase the area, then the force will decrease. If you decrease the area, then the force needed will be higher. So how we play with this, we increase the area here, we put here 5 newtons, and then we decrease the area, then the force here would be 50 newtons. Okay, so that's the part that we need so far for some applications and a quick introduction for this course. Now, before we start with the definitions, I need to specify also 3 states of substances or materials. We know that there's solid, liquid, and gases. Solid, well, I would like to ask you, but there is no one here to ask, so I'm going to answer myself. So the difference is basically we can see the atoms of the material, the solid material, they are very, very close to each other. The distance between 2 atoms, we can see if we compare it to these distances, it's much smaller. This one is very dense. Example, steel, iron. The molecules have less chance to move, and they are difficult to bend, or they are difficult to be deformed. And that's actually a very important statement here once we come to the definition of fluids and on the next slide. But in liquids we can see that this spacing is sorry, but I can't control my handwriting here. The spacing is much higher than the spacing for solids, and as we go to here, this spacing is also bigger and much higher. If we look into the molecules, they can move easier moving or transfer. And it can be deformed. For example, if we have a liquid and we put it in a pipe or duct, we can see how it would be going downwards, and then it can go in this direction. And if we have a capillary tube, for example, the fluid will flow through this and it will continue deforming its shape. So whereas if you have a solid and you try to insert it from the top here, once it touches this, if it's really hard, it can't go through. If it's a little bit flexible, so it might go, but once it reaches here, I'm sure you will have some difficulty to get it through this piping system. And finally, the gases are, once we say gases, the first thing that comes into our mind is freely moving molecules. Okay, so now we come to the definition of a fluid, and the physical definition, let me write it first. A fluid is defined as a substance that deforms under a shearing stress or force. Excuse me. So if you have a liquid here and you apply a force, if you can move, for example, your hand, if you can move your hand and you can remove part of this substance that's here, then we call it fluid. It can be gas, it can be liquid. And that actually brings me back to here, to this slide. Those two, liquids and gases, are classified as fluids. Now, if you have a solid, for example, a piece of wood or a stone, you move your hand, you can't, I doubt that you can cut this, unless if it's a very thin piece of wood and you're coming on to the thin area, you can break it. But generally speaking, we're saying you have a substance, if you can deform it by a force, then it's classified as a liquid, or as a fluid, sorry. If you can deform it, then it's under the solid category, or solid substances. More definitions. We have the units that it's not the units. This is the unit system. We have what's called the primary quantities. I've taught this course before, and most students, they have taken this in physics. So we have the three primary quantities: length, time, and mass. Length, we're going to denote L. T, we'll give it the letter T, and then mass, we'll give it the letter M. So these are called the primary quantities. So if we go to the secondary quantities, if I ask you what do you expect that to be, you would say it's a combination of those three together. So for example, So we would say it's made up of or from primary quantities for example velocity v, which is what? It's distance by time. So distance, it's length by time, so it's L times t negative 1, or we can simply leave it L over t. Or for example, we can have, if we want to know force, so that's, if we look into the Newton second law or the Newton law of motion, it's ma squared, which this one being the acceleration and m is the mass, so it's m times L over, sorry, it's m times a, t minus 2 for t squared, it's m per second square, meter per second square, so it's length per unit time, so that would be ml t minus 2. Now why we need this? Why? It might be, oh, that's so easy. It's really easy, but it's gonna be one of the most important checks for us to see if our equation is correct, our answer is correct, the work that we have done. Sometimes you will get, for example, force. If you check your units, you're gonna have meter per second. This is not force. So there's something wrong that you forgot. For example, you would have removed, or you didn't put the gravity, the density somewhere, so you'll be missing some units, and then at the end you'll have your final answer wrong. Now if you look into the table 1.1 and your book, Menson's book, so that's the first table in chapter 1, not in the book, and we have something called the FLT system and the MLT systems. Those systems are basically based on force length time or mass length time, and I have introduced this system right here, the MLT, and you can work with the FLT systems. The nice thing about this table is that it summarizes for you most of the things, the physical quantities like acceleration right here, density, energy, force, power, pressure, etc., and it gives you directly the final form of the MLT for that system. So if you have an equation and you have multiple variables or parameters or quantities, you can come back, you can always come back to this table and pick the summarized unit right here and use it for to check your equation. Let's take a quick example. So if we say we have, we don't know this, maybe you know it, maybe not, but we'll assume that you don't know it, so I give you the definition of pressure. Is defined as density times gravity times h, so it's h is the height. So if we look into this picture here, we have a pipe and we need to know how the pressure is changing along the flow. It's going from right to left, and due to pressure drop friction, so that we expect the pressure to be decreasing. But what's the relation there? We will need to do some proof and verification of derivation to reach to this equation right here. But this definition says the pressure at any point is defined as density of the liquid that's running here times the gravitational, the acceleration, times the height of the fluid inside these tubes. So is this equation right or not? The first thing that you might need to do is simply check the units, and that's what we call the homogeneous unit system checking. So pressure, what's the MLT system for pressure. So if we go back here, we look for pressure, it's right here. You can use this, but make sure if you use FLT system, use FLT system for the other side, for the right side. So it's ML -1, T -2. So we have M L -1 time -2, or we can write it as M over L T squared. Again, it doesn't make any big difference. Now the right hand side, rho GH, okay. Now density, without having to go back, it's mass per unit volume. So it's mass per volume, so it's length cube. I will go back now, because we need, if you don't know G, although we have done that. But H is simply a distance, so it's L. And then G, if you don't know G, it's what? G is the gravitational acceleration. I don't care for now about what is it exactly, what kind of gravity or the value. I'm just checking if the equation that I have here is right or wrong. So it's an acceleration. We know that acceleration is what? It's distance meter per second square. So it's meter per unit time squared. Before we do the manipulation, if you don't know the density or the acceleration for some reason, you can always go back here. That's the first one, the acceleration. The second one is the density, so it's here, so it's ML -3. Okay, so now we have ML -3, and then LT squared L, so this and this cancel out the cube, and then we're left with ML M divided by L T squared. So we can see that the right hand side and the left hand side, they are the same, so this system is homogeneous. Okay, another topic that we will jump to is the governing equations that govern the fluid or for example thermodynamics or heat transfer. What are the equations and what are the important equations for us in this course? The first one is what we know, Mr. Newton, so it's Newton's second law of motion, which is F equal force equals mass times acceleration. So that's mass and that's the acceleration. And the second one is the conservation of mass. What does that say is we have mass and it's being conserved, so nothing can be created or destroyed. It's the same as for energy, so that brings me to the third type, so it's conservation of energy, or what we call the first law of thermodynamics. Let's go back to this one right here. Which is green this time. So the conservation of mass, if we have a box or anything and we have m dot in, m dot out, they have to be equal. If not, then that means there's something being generated or lost, lost, it means it's being removed or being stored. Okay, so how we put that into mathematical manipulation is m dot n summation, because we can have, for example, 2 or 3 sources, minus everything that's leaving the system, summation of everything that's leaving, plus anything that's being generated. For example, if we have people, they generate heat, if we're talking about energy. If we have a nuclear reactor, so the fuel tubes that you have of cells, they might add some liquid, or in general, we're not talking about just liquid, anything solid, so any material that's being generated. Those three, if they're not equal, then the difference is going to be stored inside my system. So it's dm stored by dt. So the rate of storage, so we have to remove, since I'm saying you have to remove this dot. So these dots here, they represent the rate of the mass, and this one is the rate of the mass, since we have dt right here. Okay? And next, or finally, but not the end, well, the final governing equation is actually the that we need here, as what we know, we should all know, is the ideal gas law, which is P times V equals mRT. P is the pressure, V is the volume, M is the mass, R is the gas constant, and T is the temperature. Now sometimes you might see it as what? P small v, which is the specific volume, equals RT, where this V is simply V over M, so we call it the specific volume. Okay. So next, fluid properties. I'm almost there. I won't take too much time to end this lecture. So fluid properties, we have 3 properties that I would like to cover, and those are very, very important for our course. So I hope that you're with me, you're not sleeping while watching this, or you're watching a movie or something while you're listening to this lecture. The first one is density. I expect all of you know it, and you know that this rho stands for density, and it's defined as mass over volume. Okay? And as we have said, if we have specific volume, V, or V like that, it's V over M, and that stands for 1 over rho. It's simply V over M, this, so it's 1 over rho. So it's the reciprocal of the density, or the inverse of the density. Now unit-wise, this one is kilogram per meter cubed, if we're talking in SI units, or it is pound mass per cubic feet if we're dealing with British units or the English units. Now water for fluid course is going to be our reference point. So if you memorize these values, it's really helpful. Density for water at normal temperature and pressure conditions is 999 kilogram per meter cubed, or it is 1.94 in English units slug per cubic feet. Okay? And those are actually for water and air. They are on the cover page. Just flip the cover of your book and you will find table 1.5, 1.6, 1.7, and 1.8. The first 2 are for liquids, common liquids. So you have water, you have mercury, carbon tetrachloride, etc. in SI and British units, and then you have common gases in table 1.7 and 1.8 again in SI and British units. Now we come to the second definition, and this one you will see it in mostly all lectures. Specific weight. Now the way we define specific volume, it's volume per unit mass. The same thing goes for the specific weight. Now we will denote it for now just SW, specific weight, and we will define it as weight per mass. Now we know that the weight is simply a mass times acceleration. We're gonna say it's g divided by specific weight is weight per unit volume, not per unit mass. So it's how much weight you have in that volume, and the same thing goes here, specific volume, how much volume you have per unit mass, or how much mass you have per volume, and that's what we call the specific volume right here. Okay, so we have mg divided by v. Now what's m over v? We will look here. If you don't know, it's m over v, just right here, and that's going to be rho times g, and rho is density times g. Now we don't want to keep writing rho times g for a reason, which is first, most of the fluids that we will be dealing with, they might be water. If not, then we will use this guy here. And then next, g is the gravity at Earth, so we won't be actually doing applications on the moon or somewhere else. So those two are going to be constant for water, and that's why we will give it a new symbol, gamma. Now gamma, again, for our reference point for water is if you don't know it, g is almost 9.81. This one is almost, you can see it's almost 1,000. So it's 9.81. Let's work the units. So we have kilogram per meter cube times meter per second square. This one here is what? Kilogram times acceleration, so that's Newton. This one is cubed. Newton per, it's density, so it's mass per unit volume. So Newton per meter cube. Now this, that's here, times 1,000, so it's kilonewton. Since I've dropped the 9.81 times 1,000, I don't write the 1,000 here. And we would say in SI, the specific weight for water is 9.81 kilonewton per meter cube, or it's 62.4 pound force per cubic feet. Again, those two, if you look into table 1.6 and 1.5, you will find them, so you don't really have to memorize them. And then we come to the last definition, which is the specific gravity. Now it's, I don't know if you can guess what's that, but it's actually defined as the ratio of the density of the liquid that we're dealing with respect to the density of water. So now if you have any liquid and you have the specific gravity, you can easily guess what's the density of that liquid by saying it's the specific, or SG, we write it like this, S, capital S and small letter g, so it's S sub g times the density of water, which is almost 1,000, so we can get the density right here. But before we do that, actually, let me do this quick thing. So SG, specific gravity, is the density of the liquid by density of water. If we multiply and divide by g, I can do that, right? So I didn't do anything other than saying now we have rho times g, so that's the specific weight of the liquid, excuse me, divided by the specific weight for water. So now, if I give you just the specific weight of the, like an oil, a fuel, something, you can get the specific weight and you can get the density, because those numbers for water are tabulated for you in table 1.5 through 1.8. So you can get that. So we can get the specific weight and we can get the density as well by using simply the specific gravity. So the specific weight, we're going to see it's used in the coming lectures. But before I end this, I know I said I'm going to end it. Well, we still have time. It's only 35 minutes. But it's our first lecture, so I don't want to spend too much time and you guys might get bored. The final thing that I want you to know, to take from this chapter, beside the next lecture, which is viscosity, is the pressure. We have something called the absolute pressure, and we have gauge pressure. So if you have a closed tank and you put a gauge there, so this pressure that this guy is giving you is called the gauge pressure, and it's not the absolute true pressure, because we know we have here atmosphere, so it adds up to this if you open this, if this one is open. So there's a difference, so we need to differentiate between those two. And what I have just said is what we need to know. The absolute pressure is simply the gauge pressure plus atmospheric pressure. Now atmospheric pressure, we know it's almost 101 kilopascal. I know, 0.3 something, that's fine. Or it can be 14.7 psi. Those are the numbers that are like I have memorized. So if you don't know for a specific, that's for standard temperature and pressure for air. If it's something else, then we're gonna have to derive it. So let's just work this examples, and next time we will be doing viscosity. So that's my final slide for today. So what we have a cubical tank that has each side, since it's cube, so all sides are equal, and it's equal to 1 meter each, indicates a gauge pressure of 1400 kilopascal. So we have pressure right here. This pressure, since we said, they told us it's gauge pressure, so it's PG, or gauge, you can write gauge, it's 1400 kilopascal. When filled with a gas that has a specific gravity, it's G of 0.3. The gas constant R is 54 joule per kilogram Kelvin. Now let me, I did say this on Monday, and I'm gonna say it again if you were not listening or something. If I give you the units in SI, you work the problem in SI. If I give it to you in British or English units, work it in English units. Don't convert. If you convert, I'm not gonna grade it. If it's exam and you convert, you will lose time. I might grade it, but you will have some points off. Let me be clear on that. So first we need to find the, let's change the color. To red. We need to find the temperature of the gas inside the tank using ideal gas law correlation. So if we look into the correlation, it's we have given pressure, the gauge pressure inside the tank right here. So we have the gas, and this gives me the pressure right here, which is 1400. The specific gravity of this gas is given, and R is given. And we need to use simply, so I even told you to use PV equals MRT, or we can rearrange those two so that, and that's another form as well, that you guys should have used in physics. So it's rho RT, or P small v RT, and 1 over V is simply R, rho. Okay, so we need to find this guy, the temperature. What is it equal to? R is given. Density, maybe. Do we know how to get the density? The answer is yes. We have specific gravity, remember, from the previous slides. We have the specific gravity is density over density of water, or density is specific gravity times the density of water. So if we take that and we apply it here, so the density here is 0.3 times density of water. So if we take this as 1,000, since it's SI, or you can use 999, that's fine with me. Or it's more accurate actually, but the 1,000 is fine with me. And we have to say it's at room temperature. No, it's not at room temperature, sorry. We need to find the temperature. So we have the density is now 300 kilogram per cubic meter. What's next? We have the density, we got it. We have R, do we have pressure? Yes, it's 1400. Now, that's the ideal gas law, and everything has to be in absolute. For example, T has to be in Kelvin, and so the pressure. So the pressure here, we need the absolute pressure, so it's gauge pressure plus the atmospheric pressure. Now, atmospheric pressure, we know what's that, and that's where I need to say it's sea level, blah blah blah. If I don't, you can simply use the 101. Okay, so the gauge pressure is 1400 kilopascal plus 101, right? So that's 1501 kilopascal. Finally, temperature would be pressure divided by rho times R. I just want to do a quick check on the units to make sure we have the correct units. Rho is 300 kilogram per cubic meter. This one is kilopascal, so it's kilonewton per meter square. And we have the R, the gas constant, 54 joule per kilogram Kelvin. Now, what's joule? That's the question. Joule is a unit of energy. So if we have joule per second, that would be watts. That's power. So joule is the energy, which is Newton times meter. So we can remove this, put Newton meter. Okay, what do we have? So we have meter squared here with meter, and meter cubed here, kilogram with this kilogram would go, and then the Newton with Newton goes, and we're left with Kelvin because it goes up. And don't forget the kilo here, or we can remove it and multiply by 1000. Okay, so all what you have to do now is use your calculators and your magic fingers, and it should give you 92.7 Kelvin. Okay, we'll do more examples in the coming chapters. I know I have introduced too many things, but we will do some more examples for the specific weight. Specific weight is simply the a definition that you will need. You need to get familiar to the, just like what's specific weight, what's specific gravity, and we will see that in later lectures. As I've said, we will stop at on this slide this time, and we'll see you next Monday, where we'll pick it up from here. Thank you.